All right, hey everybody. So in the last video, we learned about the first fundamental form, right? And this was a bilinear form, a bilinear function defined on the tangent space of our surface at each individual point, right? And it was created to simply compute the dot product of different vectors that were in that tangent space. And we saw that this could be represented in a matrix form, right? We would typically call this matrix G. It would have these values like G11, G12, G21, G22, and these were simply going to be, for our given parameterization, capital X, we would take the two partial derivatives, x sub u and x sub v, and then our entries would just be xu dot xu, xu dot xv, xv dot xu, and xv dot xv, right? And of course, it's worth pointing out, because the dot product is symmetric, these two diagonals, the off-diagonal entries, would be identical. Because these are expressions that themselves might have u's and v's in them, what we get then is a matrix of functions, right? And at every given input u and every given input v, we would get a different, potentially different matrix as a result. Now, what we want to do in this video is talk a little bit about how we can use the first fundamental form for some geometric computations, right? And so this is really the video that we're really going to begin computing, geometric expressions, computing different things on our surface. And we're going to talk sort of completely through how to calculate the length of vectors using the first fundamental form. But similarly, we'll also be able to compute areas of vectors, and then we'll be able to compute lengths of curves on our surface, and also area of regions on our surface as well. So let's take a look. All right, the example that I want to look at is our unit sphere, right? This is our two-dimensional unit sphere sitting in three-dimensional space. And I'm going to denote that from this point forward, if I haven't already, I'm going to denote this with a sort of script S2. For our sort of two-dimensional or our surface unit sphere. And I'm going to be using our spherical coordinate parameterization. This was x of u comma v equals cosine u sine v, sine u sine v, and then cosine v, right? And so this would map the sort of patch in uv space from 0 to 2 pi in the u direction, 0 to pi in the v direction, onto our unit sphere. And so we could first compute our first fundamental form, right, by taking the u derivative, taking the v derivative, and then actually computing the individual entries. And so that's what we do down here. So for example, our first entry in this matrix, the G11 entry, would be x sub u dotted with x sub u. And we see that becomes sine of u squared times sine of v squared. That's this times this. Plus cosine of u squared, sine of v squared. That's this times this. And then plus 0 times 0. So we would get that as our entry. Of course, because of the Pythagorean trig identity, we can simplify this down, and the end result is just the function sine of v quantity squared, right, or sine squared of v. So our first entry in our matrix, the G11 entry, would just be sine squared of v. And of course, as we plug in different v values, that entry would change depending on v. Now, our off-diagonal entries, G12 and G21, can be computed as similarly. In this case, we actually get some great cancellation. Everything cancels out, and those entries are going to be 0. And then for our G22 entry, that's going to be x sub v dotted with x sub v. We're just going to take this vector dotted with itself, and we will get cosine squared u cosine squared v plus sine squared u cosine squared v plus sine squared v. And again, there's going to be some excellent cancellation because of the Pythagorean identity. This will all simplify down to 1. So when the dust settles, we see that our matrix G, right, our first fundamental form, takes on this form, right? And so this is the associated matrix for this parameterization of the sphere. Okay, great. So with that as our first fundamental form, then, how can we use it to compute something interesting? All right, well, this is the question that we're going to be interested in answering. At the point on the sphere that corresponds to the point in the domain, pi over 4 comma pi over 4, what is the length of the vector x sub u plus x sub v? Right, so this is a point, right? Let's be clear. pi over 4, that's a point in our domain space here. But after we map that via our parameterization, that's going to be a point on the sphere. X sub u is going to be a vector in the tangent space out here. X sub v is going to be a vector in the tangent space out here. So xu plus xv will be a vector over here in three-dimensional space, and we might be interested in knowing how to compute its length. So before we had the first fundamental form, our only path forward would be to do this, right? We would compute x sub u, and this time we would plug in, pi over 4 for our u value, pi over 4 for our v value, and when we plug these in, we simplify down to get negative 1/2, comma 1/2, comma 0. So that is our x sub u vector at the point right here, right? And so that's going to be maybe sort of like this vector right here. That's my x sub u. Now my x sub v would be similarly computed. That becomes 1/2, comma 1/2, comma negative 1 over root 2. So that's another vector over here. Both of these lie in the tangent space, so I would add them together. I get a new vector in my tangent space. Maybe x sub u plus x sub v is this third vector. And then I would compute its length, right? And of course, in this case, the vector that we get as a result is the vector 0, comma 1, comma 1 over root 2. And if I go to compute that length, that's just going to be the square root of 0 squared plus 1 squared plus 1 over root 2 squared. So that's going to be the square root of 3/2. Right? And so that vector that we're interested in will have a length of the square root of 3/2. Okay, so now that I have the first fundamental form in my toolbox, how can I compute this using the first fundamental form? Well, the first thing that I want to do is I want to represent the vector I'm interested in a particular notation, right? So x sub u plus x sub v. Well, x sub u, right, I drew it over here in 3 space, but its corresponding vector in the domain was just the vector 1, comma 0, that vector right there. Similarly, x sub v is the vector pointing up in the v direction. That's that vector there, 0, comma 1. And so the vector x sub u plus x sub v in the domain space could be represented as those two vectors being added together. That is the vector 1, comma 1. In other words, I could identify that the vector x sub u plus x sub v can also be thought of as the vector 1 x sub u plus 1 x sub v. And so I can represent that using the sort of in vector notation or in matrix notation using the column vector 1, 1. So the vector we're interested in, is going to be represented as 1, 1. Right, where again, this one up here means that this is a 1 x sub u, and this one down here means that that is plus a 1 x sub v. Right, so to use a little bit of linear algebra language, we are representing our vector in question as 1, 1 when using the x sub u, comma x sub v basis. Right? But at minimum, we just have to remember that this is supposed to represent 1 x sub u plus 1 x sub v. Now, with that in question, or with that out of the way, our first fundamental form can be used to compute the dot product of this vector with itself, which we can then take the square root of to get the length. Right? So in particular, the length we are interested in is equal to the square root of that vector dotted with itself. And according to our new notation, we can compute that by computing the first fundamental form of v dotted with itself, right? So the vector in question dotted with itself. So we're interested in taking the square root of that first fundamental form. Now, to compute the first fundamental form, and let's slide up here a little bit, to compute that first fundamental form, we would take v transpose, right? So this will be the square root of all this, be v transpose times our matrix in question, G, times v by itself again, right? And so we can really denote that as the vector, the vector 1, 1, the matrix G that we computed before, so that was sine squared of v, which I guess we could actually simplify, right? V is pi over 4, so sine squared of v would be the square of root 2 over 2, and so this is really just 1/2, 0, 0, and then 1. So we have v transpose times this first fundamental form at the point pi over 4 times our original column vector here. And then we're taking the square root of all of that. All right, so now it just becomes a matrix computation. And our matrix computation, right, would be, if I multiply all of this out, this would be the square root of, I'll keep my 1, 1 here. This will become 1/2 and then 1. All right, and then that just becomes 1 times 1/2 plus 1 times 1. So that whole thing just becomes the square root of 3/2, exactly like we had before. Right, so rather than having to compute all of these vectors and figure out what they are at pi over 4, comma pi over 4, and then go through this computation, if we have our matrix, right, our first fundamental form, we can compute the length of this vector just by using the first fundamental form and then taking the appropriate square root. And we end up with the same answer both ways. All right. So it turns out that this idea of using the first fundamental form to compute geometric quantities can be extended into a lot of different directions. And here we identify 2 of them. Right? First, let's say or I should say in both of these, let's take a region in our domain space and let's have it mapping to a surface S. And that's going to be through a parameterization capital X. So that should be a capital X right there. Let's have an associated first fundamental form. This is our matrix G, right? And so let's assume that we can compute that at any point as G11, G12, G21, and G22. Right? Then we can compute lengths of curves and we can compute areas as follows. First, when it comes to lengths, let's pretend that we have a curve gamma of t, right? So this is a gamma of t, and that's given as the parameterization of another curve alpha of t. So the setup here, right, is that I'm going to have an alpha of t here in my domain space. Right? So here's my alpha of t. And then that curve gets mapped by my parameterization to this 3-dimensional curve, right, or this space curve over here. And this is going to be my curve gamma. Right? And so that is my curve gamma of t. Right? So we have alpha of t mapping to gamma of t. And let's say that we wanted to measure the length of gamma of t. Right? That's our length of our space curve over here. Well, it turns out we can compute that by computing an appropriate integral over here. Right? So the length of gamma will be computed. We know we can compute it using our regular integral, right? This is what we would have done before this moment. Just computed the integral of the speed in 3-dimensional space, right? So the integral of gamma prime. But we now know that we can compute this using the first fundamental form evaluated at each point of alpha prime comma alpha prime, right? So I can now compute this just by looking in this coordinate system right here, just looking in this U and computing the first fundamental form at each appropriate point with the vector that I'm plugging in corresponding to alpha prime. All right, now similarly, right, I can use that for area. Just erase this quickly. Okay, if I can use that for area, or for length, I can also find area of regions by creating an appropriate integral to compute. So specifically, if I have a region Q in my domain space, so maybe this is my region Q right here, right? So there's that nice area all in there. That's my region Q. And if I take the image of that right? So I get some sort of region up here, right? And maybe this is my region Q. Up here, I can find the surface area for this region by computing an appropriate integral over my domain region Q. Specifically, the area, the surface area of this piece over here is going to be the double integral over my region Q of the square root of the determinant of G. So the square root of the determinant of my first fundamental form. Now, to compute this, right, this will be a double integral, which will involve some multivariable integration, but we are integrating over just a subset of a two-dimensional space, right? So this is just a subset of R2, and so we can compute that integral in a very relatively straightforward manner, and so we can get this surface integral as a result. These types of computations, right, the computations on our surface of area or of length that come from actually computing an expression over the domain space, right, these are called intrinsic measurements of our surface, right, in the sense that once I've pulled back to my domain space and I'm just computing this area, or I'm computing the length over this region in U, I'm really just looking at my coordinate patch, and I'm not really paying attention to where this, I should say I'm looking at my sort of subset U, and I'm not looking at where the surface is physically sitting inside of three-dimensional space. Right? So it's called an intrinsic geometric computation, and the first fundamental form is what allows us to compute such intrinsic expressions.